Hello guys, so in this video we'll be dealing with how you can make a Mod-7 counter using JK flip-flop, a Mod-7 Synchronous Counter using JK flip-flop. So the logic which I'm going to show you in this video would be applicable to all of the other mod counters that you want to build. Suppose you want to make a Mod-9 counter or Mod-11 counter, or let's say 1357 counter or 2468 counter. Any counter that you want to build, you can build using the same logic. Okay, so let's just start with the session. So today we'll be dealing with Mod-7 Synchronous Counter. Okay, so we'll be building this synchronous counter using JK flip-flop. Okay, JK flip-flop. But you can also build this counter using a T flip-flop or a T flip-flop, no matter what the flip-flop is. Basically, the T flip-flop is the most easiest one, and we'll be using the logic of T flip-flop further in this video, which I'll be showing you. So just sit back and wait for it. So to build a mod counter, any mod number counter, there are some steps that you need to follow. So the first step is know the number of bits needed. So you have to first of all know the number of bits that you would require to build a Mod-7 counter. Okay, so what according to you could be the least number of bits that would be needed to make a Mod-7 counter? Yes, you guessed it right. You need 3 bits to make a Mod-7 counter. Why is it so? Because see, using 3 bits we can represent at most 7 number in decimal, because the least significant bit represents 1 or holds 1 value, and the middlemost bit represents 2 as its value, and the most significant bit represents 4 as its the highest value. So if all of the 3 bits are, let's say, 1 1 1, then in decimal that would be equivalent to 7. Oh sorry, that would be equivalent to 7. And see, we want to build a Mod-7 counter, right? So according to this, we would only be needed to show 0 to 6 numbers on some display, which I'll be showing you further on this video in Logisim. Okay, how you will building this circuit in Logisim, and it will work also. So for that you need to do some calculation, which I am showing you. So okay, so we just need to show at most 6. Okay, 0 to 6. So what is 6 in binary? So 6 in binary is 1 1 0. 1 1 0 is equivalent to 6. Okay, so the number of bits that would be needed would be 3. Okay, so if you need 3 bits, now you know how much bits least number of bits you require. So the next step is to know the number of flip-flops needed. This is very simple, because number of flip-flops is equivalent to number of bits. So we just figure out that we would require 3 bits to show values ranging from 0 to 6, right? So we will be needing 3 flip-flops to make this circuit. So the number of flip-flops are 3. So we'll be using 3 JK flip-flops for this experiment. Now the third step is draw the excitation table of the flip-flop. So since we are going to use JK flip-flop for this experiment, there is one catch in this experiment. I've told you in the beginning of this lecture that we'll be using a concept of T flip-flop. So this concept now comes into the picture. So how we'll be using the logic of T flip-flop into JK flip-flop. So you might know this, that a JK flip-flop, JK clock, Q bar, QN bar, JK. A JK flip-flop can be converted into a T flip-flop simply by connecting its J and K terminal together. By joining its J and K terminal together, this would be equivalent to a T flip-flop. This will perform similar to a T flip-flop. So now what we just need to do is draw the excitation table of T flip-flop. We'll be using JK flip-flop for this experiment, but we'll be using T flip-flop's logic for this experiment. So let's just draw T flip-flop excitation table, because excitation table of JK flip-flop is a bit complex. Okay, see, I can also draw an excitation table of a JK flip-flop, but using that table would be a lot of tedious work to do in the further steps, which you will be realizing soon. Okay, so let me just make the truth excitation table of JK flip-flop. So the excitation table of a JK flip-flop looks something like this. Okay, so if you make this, or if you use this table, the state table which you'll be building in the further steps would having a lot more columns than using a simple T flip-flop's excitation table. So see, 0 0 0 1 1 0 1 1. So this is the excitation table of a T flip-flop. So when this, how can you remember this table? See, the previous state is 0 and the next state is 1. This means that the T flip-flop would be on toggle state, right? Because the output has toggled in its next state, right? So the T flip-flop's input must have been 1 to make this state toggle. Okay. Similarly, in this row, the previous state is 1 and the next state is 0. This also means that the T input should have been 1 to make this state toggle, right? So you can remember it like this: 0 1 1 0. Okay. So this is a pretty simple table which you can use to derive the Boolean expressions. Okay. So now let me just change the paper. So the fourth step that you need to do is a state diagram. You need to make a state diagram first. What is a state diagram, sir? Sir, a state diagram is nothing but it is the representation of the digits or the or the numbers that you want to show on the display. So what we are supposed to do here, we are supposed to show 0 to 6 numbers on a display. We'll be figuring out how we can do it in Logisim. Just sit back and just observe what is going on. So we need to display 0 to 6. So what our first state is, it's 0 0 0, right? Because 0 in binary is 0 0 0. Then our next state would be 0 0 1, right? Our next state would be 0 1 0. Our next state would be 0 1 1. Our next state would be 1 0 0. Our next state would be 1 0 1. So the final state would be 1 1 0. So these are all the 7 numbers that we are going to display on a display. Okay, so 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0. So our counter should work like this manner. Okay, like in this manner. Okay, so it should display 0 first, then it should display 1, then 2, then 3, then 4, then 5, then 6. So these are all 7 states, because we are building a Mod-7 counter. Okay, so now our next step is to make a state table using this state diagram. State table state table. So what is the state table? Nothing. See, since we need 3 flip-flops for this experiment, there would be 3 individual columns for all the 3 flip-flops. So the first column would be Q3. Let me just first complete the table so it would be more clearer to you why we use these terms. Q3 plus, Q2 plus, Q1 plus, T3 plus, T2. Oh my god, not T3, T2 plus, T3, T2 and T1. Okay, so I think that should be fine. So see, what is Q3? Sorry for the interruption, guys. So let me just make it clear to you that what is Q3? These Q3, Q3 plus and T3 relates to a single flip-flop, which is the see. All of our flip-flops would be arranged like this manner, okay, like in this manner. So this is the flip-flop that would represent the most significant bit. This is the flip-flop that would represent the least significant bit. I'll show you in the Logisim when I'll be making the circuit, okay. So this MSB is the T3 flip-flop. I named it T3 for my convention, okay. And this one is the T1, okay. Or you can simply take it at T2, T1, T0. This is also the general convention that is followed. So we'll be using T3, T2, T1, okay. So this Q3 is the previous state of this T3 flip-flop, and the Q3 plus is the next state for this T3 flip-flop. Okay, now it would be much clearer to you what are these columns representing. So we'll be just building this, filling up this state table using the excitation table of T flip-flop. But we just need to take care of what values needed to be filled in these rows that would be equal to this state diagram that we just built. So what is our first value that Q3, Q2, Q1 will hold? It is 0, 0, 0. Okay, so it is 0, 0, 0. So this is the initial value. So the next value from which the counter will display from 0, 0, 0 to is 0, 0, 1. So it is 0, 0, 1. So this state would act as a current state for the next states, and the next state for this state would be 0, 0, 1, 0, 1, 0. I'm sorry, 0, 1, 0. Okay, similarly 0, 1, 0. What is the next state after this? 0, 1, 0, then 0, 1, 1, 0, 1, 1. Sorry for the background noise, guys. I can't do anything. I don't have a much good setup for shooting video, but I hope it is going smoothly. So this next state 0, 1, 1. So what is the next state after 0, 1, 1? Our next state is 1, 0, 0. Then this is the current state. Then what is our next state? 0, 1, 0, 1, 0, 1, 1, 0, 1. Similarly 1, 0, 1. 1, 1, 0, right? 1, 0, 1, 1, 1, 0. Then don't forget to add this last step, which most students forget, is writing this state 0, 1, 0. Then our counter should reset to 0, 0, 0 to work in a loop. Okay, so this row is important. So now we just need to fill T3, T2 and T1 columns according to the state table, excitation table. So what you just need to keep this thing in mind is when these two terms Q1 and Q1 plus 1 are opposite or unequal, then T value would be 1. Otherwise, if both are equal, then T would be 0. Okay. So now using the same logic, we can fill up this table. See, compare Q3 and Q3 plus for this T3 column. Okay, see, this is 0 and this one is 0. So T3 would be 0. Now see the next values. This is 0, this is 0. So our T3 would be 0. See the next value 0, 0. So this will be 0. See the next value 0, 1. Okay, so it is changing. This means toggle state. This means 1. So now this is not changing. 1, 1. So this is 0. This is 0. This is toggling. Okay, 1 to 0 in the next state. So the T3 value would be 1. Similarly, for Q2, we have to fill the T2 column. See, this is 0. This is 0. So it would be 0. Again, see, this is toggling. So it would be 1. This is not toggling. So it is 0. This is toggling. So it would be 1. This is not toggling. This is toggling. This is also toggling. So now the last columns. So this is 0. This is 1. This means T1 was on toggling state. Now this is 1. This is 0. T1 was on toggling state. This is 1. This is 0. 1. Toggling, 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 and not toggling. Okay, so we have completed with our T3, T2, T1 columns. Now, what is our next step? We need to find the Boolean expression of T3, T2, and T1 in terms of Q3, Q2, Q1. Q3, Q2, Q1. Okay, remember to make the Boolean expression in form of Q3, Q2, Q1, not Q3 plus, Q2 plus, and Q1 plus. Okay, because this is the current state on which our counter would work on. Okay, so our next step is we'll be using Karlov maps or K maps to derive T3, T2, T1. Okay, now let's just fill the K maps for all T3. So this would be a 4, 3 cross 2 K map. Okay. So it would be like this: Q3, Q2, Q1. Okay, so this is the I'm sorry, 2 cross 4 K map. Okay, so this will be 3 2 the T3, then T2. I should for this. Okay, so yes, this is for the T3, then T2. So this is 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. You might be wondering what we have to do with this 7th element, because 7 is not even included in our table, right? This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So simply just take 7 as a don't care term. Don't care. That will help in our K map. Okay. So now let's just fill this 2 K maps for now. So according to the state table, what is T3? So it's 0, 0 on 0, 0, 0. So 0 on this 0, this is 1, 0, 0, 0, 1, 1, 1, 1, 0. So it is 0, 0, 0, 1, 0, 0, 0, 1. Right, 0, 0, 1, 0, 0, 1. Oh, sorry. I filled this schema. 0, 0, 1, 0, 1, 0, 0, 1. 0, 0, 0, 1, 0, 0, 1. Okay, so now let's just fill this T3, T2, 0, 1, 0, 1, 0, 1, then 1. So 3 times 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, then 1. Then 1. So this is our K-map for T2, and this is T3. So now we just have to form pairs. So our first pair would be this one, and our second pair would be this one. Right. So from this pair, we get the equation as Q3, Q2, and from this pair we get the equation as what is the equation? Q3, Q2, Q1. So Q2, Q1 plus Q3, Q2. This is our Boolean expression for T3. Okay, Q2, Q1, Q2, Q1 plus Q3, Q2. Right. So now in this table we have this pair of four ones, right? So this is our one pair and this is our second pair. Okay, so this is our second pair and this is our first pair, right? So from this big pair, so we get the equation as Q1, Q1, and from this pair we get the equation as Q3, Q2. So this is Q1 plus Q3, Q2, right? Let me just verify it. Q3, Q2. Okay, and this is Q1. Okay. So yes, we got the equations for T3 and T2, which is this and this. So now let's just derive the equation for T1, and we will be on our final step of making the circuit diagram. So I have to quickly filled all these tables. So now I filled all these cells. So now we just need to make pair out of this. So what pairs can we make? Can you figure out something? Yes. So we can make this one as our first pair, these four, and these two as our second pair. So yes, from the first pair we get our equation as Q3 bar, right? And from the second pair we get our equation as Q3, Q2 bar, right? So this is our equation. So our final equations for all the T flip-flops are T3, T2, T1. So T1 is Q3, Q2 bar plus Q3 bar. So these are our final expressions. So now what we have to do is just build our circuit in Logisim. So the next session, the next video, the next screencast would be of my laptop showing you Logisim simulator and how you can build this circuit. Okay, so we'll be just using these three equations over there and make our final Mod-7 counter. So let's just shift to Logisim. So guys, now I am on my Logisim simulator. So for the ease of use, I have already written all of the Boolean expressions for T3, T2 and T1 beforehand, so that it would be easy for us to make the circuit by just seeing all these expressions right here. So this is T3, this is T2 and this is T1. So we'll be using these Boolean expressions to build our circuit now in Logisim. Okay, so what we'll be using in this circuit as a main component is in the input and output section, which is the hex digit display. So this is the display which we'll be using so in order to show the different outputs ranging from 0 to 6 as our output. Okay, so now these are our JK flip-flops, guys. So we'll be using JK flip-flop. Oh my gosh, JK flip-flop in this tutorial, as we mentioned in our previous section, that JK flip-flop can be converted to T flip-flop by just combining. So let me just zoom it in a bit so that it will be clearer. Now it's okay. So let me just align all of these JK flip-flops. So these are our main components of using JK flip-flops. Oh my gosh, JKFs. Okay, so I have taken 3 JKFs. Okay, why? Because as mentioned earlier, we will be requiring 3 bits to show the output. So I have taken 3 JK flip-flops. I have connected the J and T terminals so that it would work as a T flip-flop. Okay, so now let me just make this a little bit more nice. Okay, so I'm done. So now we can do is just connect all these clock terminals to a same clock input, because this is a synchronous counter, and in synchronous counter the clock of all of the flip-flops are same, so that they all are in sync. So now let's take our clock from here, from the wiring section, and we have applied the clock to all these 3 flip-flops. Now just name this as CLK. So this is our clock. So now what we can do is we can connect these small reset terminals, which is denoted by R on the flip-flops, so that if we want to get back to 000 state, we can just reset our all of the outputs. So this is the input terminal for the reset, which when on takes our outputs to 000 state. Okay, so now let's just also connect, oh my gosh, let me just control Z. Let's just also connect the set terminal, so that if we want to display the most highest number, which is the 6, so we can just do it by set terminal. Okay, so this is the set terminal. Although we might not need these terminals, we can still connect them in order to, some professors can cut your marks if you don't mention these set and reset terminals. So it might be good to take it into consideration. So now I have written T3, T2, T1 in front of all of these flip-flops. So now we just need to connect these terminals as our Boolean expression. So our first expression for T3 says that we want Q2, Q1 plus Q3, Q2, which means Q2, Q1 are being AND together. Okay, they are connected by an AND gate, which further is being OR gate by a Q3, Q2, which is inside a and different AND gate. Okay, so Q3 and Q2 are AND together, Q2 and Q1 are AND together, and their outputs are being ORed together. Okay, so where is my Q2? This is my Q2 because this is T2, so their output will be Q2. So this is our Q2. Let me just take it out. So now I have taken out Q1. So these are the 2 terminals, Q2 and Q1. So we just need to AND both of them and connect with an AND gate. So now let me just change the direction and make it a little bit small. So yes, they are now AND together. So this is the Q2, Q1. Let me just name it just for ease of reading purpose. So this is Q2, Q1. Okay, so now what we need to do is we need to take out this output, and now what we are supposed to do is Q3, Q2. So Q3, Q2. So this is Q3. Let me just take out Q3 from this terminal. So this is Q3, and this terminal is Q2. So we can take both of them out, and now they can be AND together. So this is our AND gate. Let's make the size a bit small. So this is Q3, Q2, right? So let me just name it Q3, Q2. Oh my gosh, Q2. Okay, so this is Q3, Q2. So now we can finally AND to both of them. Okay, or both of them. Okay, in order to get their sum. So this is our OR gate. Oh my gosh, what's happening here? Just a second, guys. So let me do that again. So this is our OR gate. Okay, I think the medium size should be good. So this is our OR gate. We can finally connect its output to T3. So our T3 is finally done. So now let's move on to T2, which is Q1 plus Q3 Q2. So Q3 Q2, where can we find Q3 Q2, guys? Can you find it out? So yes, Q3 Q2 can be find out from the AND gate, which is over here, which we have already done in the T3 state. So Q3 Q2 can be withdrawn from this output terminal of this AND gate, and Q1 can be derived from these terminals. So these two terminals can be used. These two terminals can be used to, or both of them, to get our desired output. So we can just simply place an OR gate over here, and we can just simply connect these two terminals. So now our output is ready and can be connected to T2. So our T2 is also done. So it might get a little bit messy from this step. So no matter how it's getting messer or nicer, it's all upon you. You can make the circuit even more cleaner. Okay. So now that doesn't matter to the professor. It should work. Okay, it should work fine. So now our goal is to make T1. So T1, I'm making T1 as from the Boolean expression. So this is the Q2 bar and Q3. So Q2 bar can be get from this second terminal of T2's output. So these two will be AND. And these two can be AND from here. Let me just adjust it real quick. So this is the much neat way to make these AND operations. Okay, so yes, so this is Q3 Q2 bar. So now we just need to connect Q3 bar, and we just need to get their OR operation. Okay, so I've taken an OR gate, a small OR gate. So now I'll be just connecting this OR gate to our T1 terminal. Oh my gosh, just a second. So this is our T1 terminal. So all the three terminals are now done. Let's go. So our circuit now will be working, but how will we displaying the output? We have not connected our hex display yet. Okay, so these all are done. So we can now just connect the hex display. So let me just name it real quick, because if I want to share this this file to all of you, it would be conventional for reading purpose. Okay, so now we just need to take out the Q3 Q2 Q1 and connect it with a hex display. So let me show you how to do that. We need a hex digit display over here, and this hex digit display can be taken in the multiple inputs and converted into a single output by a splitter. So a splitter is a magical thing which takes some input and returns a bandwidth output. So we need to set the bandwidth of this splitter as 4. Okay, because the bandwidth of the input terminal for hex digit display is 4. So let me just change it. So this is our hex digit display. Okay, so this is our band splitter. So we can just change it to 4, and then we can change the fan out to 4, because these two values must be same. Okay, must be same. Not in all cases, but mostly it should be same. So 4 we can just ignore the third terminal, and we can just connect the T3 T2 T1 to the second, first and 0th terminal of this splitter. So let me just make it real. Now for the final third terminal, I mean the first, which is third, we can just connect it to a ground. Okay, so we don't need that. So now let's just connect our output to the hex display, and we can see that the hex display is currently displaying 0 as its output. Okay, so our circuit is finally done. Let me just make the auto tick frequency a little bit higher, so that we can get the outputs a bit faster manner, in a bit faster manner. So our circuit is finally done. We just need to press Ctrl K to activate or trigger the clock. So let me just press Ctrl K, and your circuit is finally done. It should be working very fine. So yeah, let's just see it's working. So I'm pressing. Hooray guys, you have finally learned how to make a Mod-7 counter. You can see the hex digit display is showing from values from 0 to 6 clearly. Okay, so using the similar process, you can make a Mod 9, Mod 11, Mod 10, any Mod counter, guys, any Mod counter using the same process. So I'm giving you this as a homework. You have to make a Mod 9 and a 2468 counter by your own. Okay, so you can just make it, and you can just show me, either mention me on Instagram. I will repost your story if you make it, and I would be really happy to see all of you guys making your circuits on your own. So I hope you like this video. If you enjoyed, make sure to like. If you have missed any part or didn't understand, you can ask your doubts anytime in the comment section. I will be replying as soon as possible. So that's it for this video.